So the topic is Taylor polynomials. It's just a word that is used to describe the might hide what we're actually after actually, if you want to describe what we're trying to accomplish, is approximation, and we're approximating functions with polynomials. So because polynomials are simplest functions to compute, so that's the choice, our choice for approximations. So a linear approximation is simply the degree 1 Taylor polynomial. The linear approximation that you saw in calculus 1 is simply degree 1 Taylor approximation. Okay, so I think you will. I hope you'll find this somewhat straightforward, but only if you are really very comfortable with differentiation and all the topics that surround it. So, so as you can see, the computation that we did yesterday were like this. For example, is nothing but differentiation. Differentiation, going from right to left, or going down first differentiation, and then from right to left, we just substitute things. We substitute things, and then we divide by the factorial. That gives me right away all the coefficients of my Taylor polynomial. Okay, so that's all there is. So the challenge then is differentiation. Beyond that, maybe for this particular example, in fact, not just differentiating infinitely many times. That I suppose is the challenge. The one we did at the end of yesterday was exponential function. That is easy to differentiate. There is no change. Same function every time. With trig functions such as sine and cosine, it's slightly more complicated. And you can see can you see the pattern of differentiation of trig functions? Starting cosine. What's the pattern? In the first column, what do you see? We don't have. Well, you can guess what the fifth line is. What's the fifth line? Negative sign. So, well, how do you know? Well, because you differentiate a cosine, but we already differentiated cosine once, so we know that it's going to be repeating itself. So in fact, this is the block that will be repeated infinitely many times. So, and that's the beginning of the next block, and it will be 4 at a time repeating itself. And so as a result, what's going to happen is the block over here will also be repeated, right? Once we substitute the values into the function, there will be repeated. So it will be 1 0 negative 1 0, and then on and on, repeating those numbers. So these will be for example, zeros. Look at the zeros. It means that the zeros, the odd numbered derivatives will give us 0. So there will be missing coefficients with odd degrees, just as if we look at T4, as you can see, this is what I'm talking about. This is missing and that is missing. The powers with odd degrees will be missing every time, which is not entirely surprising, because cosine is an even function. Okay, and that picture that we saw yesterday is applicable. Okay, so these are all the approximation that we have computed. Why is it not working? This one is also not working. Okay, so as you can see, all the approximations are also even. So even where does the word even comes from? It comes from even degree. So even degree polynomials are only the ones that we can see. Nothing odd degree polynomials are out of the question, because they're just behave so differently from the even function. So as I said, there will be only even what I'm saying is that we'll be skipping the degrees. Odd degrees will be skipped. Okay, so that's a pattern that you notice. Otherwise you can also notice another pattern, and that is the terms that do appear, they will alternate signs. So it will be 1, 0, negative 1, 0 means that once again skipping terms, but the rest of the terms will alternate in sign. Okay, so that's differentiation taken infinitely many times. So it's certainly not easy, and we don't have too many functions that actually can be subject to such analysis. It's either sine cosine. It is the exponential function, the simplest one, and some powers. So for example, you can do the same thing with 1/x. You can imagine you differentiate 1/x, and you keep differentiating. The power will be going down, 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 and you will simply notice the pattern. Okay, so just taking care of the coefficients, the only challenging part, but that is the challenge. So what I'm talking about is 1/x prime is equal to negative 1/x squared, and then you differentiate one more time. It will be 1 over 2 over x cubed, and so on. That is infinitely many times differentiation. You'll see how those numbers will be accumulating. Numbers in the numerator will be accumulating, right? What's the next term? It will be 2 times 3 over x to the 4th negative sign. Okay, so and on and on. Okay, so that's an example of that. You can try to take it to the next level. Okay, so so that we might revisit later, but right now let's take another look at the analysis that is complete. So not just up to some degree that we have picked randomly, such as this. We just decided let's do T4 and we stopped. Here we did not stop. We went n degrees into the future. So all the terms that we can imagine are available, and we can approximate it with any degree that we can. Put any standard that we put in front of ourselves, we can meet. Okay, so that is the other picture that I showed you last time of approximation of the exponential function. That actually very strong. A strong indication of how approximations increase. So the function that we are approximating is in green. This. Okay, so that is my function, and you can see it early on when you approximate with a linear function, which is the one that I'm pointing out. This one, or previously constant function. The things are. You can see the separation. You can see how far we are from the truth. So once again, pointing out the errors right here. However, as we move on, the gap becomes smaller and smaller, especially on the right. Look at it. This one is this one is T4, and the difference between the green and red is almost invisible. There is somewhere over there, there is some error, but it's virtually invisible. And as you go on, invisible, invisible, invisible. They literally merge with the graph. Not so on the left. So the function is growing infinitely fast on the right, or if not infinitely fast, but faster than any polynomial. But as long as we pick a large degree large enough, they will be virtually identical to the right. Why? Because a polynomial does grow to infinity, even though not as fast as the exponential function. So once again, this is the exponential function e to the x. Okay. So then, even though over here they will separate at some point, it might take a while. However, on the left, that's the trouble. No matter how hard we try, there will be always a big separation. Why? Because the polynomial always goes to infinity, while the exponential function at the negative infinity, it has a horizontal asymptote. So even though we try to get better and better, and we can see that the behavior around in this area is getting better and better. However, it will never be ideal, because polynomial will eventually go to infinity. You can notice also how it alternates between negative and positive infinity, because we skip between odd degree and even degree polynomials. So on the left we either go to plus infinity over here or we go to minus infinity. Why? Because this is T6. Why is it? Oh, it's not T6. T3. I'm sorry. This is T3 over here. T4 and T5. So odd degree polynomials behave differently from even degree polynomials. So you might remember that from pre-calculus. Even degree, a polynomial looks like this or like that. Okay, so it might oscillate somewhere in the middle, but large scale behavior is infinity, either both of them positive or both of them negative infinity. With odd degree, it is the not the opposite, but rather the infinities are different. So odd degree would behave like this or like that. So it might have in the middle many x-intercepts. It doesn't matter. Large scale behavior, that's what it looks like. It goes from one infinity to the next, to the other. Okay. So and that's what you see in this picture. If we are switching between, we have to switch between two different odd, even, uneven. That's we keep going. T6, T7. You can see how behavior changes here from plus infinity to minus infinity. Odd degree, even degree polynomial. At best, so it also oscillated. You can see the difference between T6 and T7 is huge. On the left, it drops from one infinity to the other. That once again emphasizes the point that we only care about what's happening here somewhere, around the point where we approximate. Okay, so that is just for you to do a few exercises of computation of Taylor polynomials, either a few of them or all of them, as in the last case. But actually what we care about right now is actually understanding approximations. So what is an approximation? That the word that is used very casually, but even though we have pointed out what is that we're talking about, but we didn't say what it is. What does it mean to approximate a number? And just to say some loose words with we're getting closer to some number, to the truth, is really not enough. For example, once again we're talking about the square root of 4.1 that we started with. And then we said the answer was like 2.025 or something like that. It is approximately equal to, but that really doesn't help us. So that's what we started with, we produced the answer. But just to say that it's approximately equal to is meaningless unless you can tell how close. So how close? You say it's close, but how close? Why do you care about how close? Because you really you got to point out where the truth is. So if all you supplied with is this number, you cannot really tell where the truth is, because it's not the same number as the one that you're looking for. It's only an approximate number. So then how do you know where the actual number is? So how do you resolve this? So approximation should not be just a number, but rather what? A range of numbers, right. So instead of this is very incomplete. It is one number, and we do not know how close we are to the truth. So give a range of numbers, typically an interval. And then if it is an interval, then make sure that it is the interval that contains the truth. Okay, so say this is we don't know where the truth is, but we know that it is within this interval. Then it becomes clear what it means to improve the approximation. You make that interval smaller. And so you are zooming in closer and closer on the truth. You will never find the truth unless you actually take the limit. And if you talk about approximation, that's not a possibility, but the theory that tells you that it is possible is still crucial. So you can get as close as you like to the truth by these approximations. So your approximation might be, say, maybe this number 2.025 is here, but the truth is here somewhere, and we don't know where it is. The truth meaning the actual value of the square root of 4.1, somewhere within the range of values. So we need a range of values. Sometimes you certainly have seen it elsewhere. It is usually given by plus or minus. Okay, so for example, it is everywhere. So for example, if you look at the thermometer, it will give you, say, 90 degrees, and it always, even if you ignore the actual error contained in the quality of your measurements, just the presence of the scale indicates that you cannot do better than, say, plus or minus 1 degree, because it does not have smaller. A regular thermometer does not have smaller markings, so you cannot tell with any more accuracy than that. And so that comes with the territory. This is a range, so it will be actually 89, 91. Okay, so if somebody tells you it's 90 degrees, that in reality there is some range, and the range is probably the safe way to safe to assume that it will be between either an 89 and 91, or maybe it will be plus or minus half degree if you can separate the two markings from each other. Then it could be smaller. But the point is, it's providing ranges of values for everything that is not exactly computed. And let's face it, it's never exactly computed. Is done in any sciences or engineering routinely. Okay, so and then the difference what mathematics gives you is that we could, as I mentioned, we can have any accuracy. We should be able to provide any accuracy for computations, because there is everything that we need to know. There is a way to find out, at least at better and better degrees, and that's degrees literally the degrees of those Taylor polynomials that we have. So if we can, with the exponential function, increase the accuracy, that's how we increase it. We'll increase the degree of Taylor polynomial. Which the trade-off is that you will have more computations, but you'll get more and more accuracy, and that range of values will be smaller and smaller and smaller. Okay. So so what is there is an error bound for our estimation. So this one will be accompanied, the approximation will be accompanied by a plus or minus information, a plus or minus number, and that number is called an error bound. Plus or minus the error bound. Well, the formula is found based on the following idea, which is you can see it in the lower dimensions. If you have your function, okay, and you have a linear approximation, okay, so this is a linear approximation. In other words, it's a t1, and this is your function. This is your function, okay. Y equal f of x. Okay, so then the degree of your error is determined by how far your function f of x is pulling out away from your linear function. This is what is determined by. What makes the question that we should ask, what makes f turn away from its tangent line? So this is my A, okay, and so the question is, you can think about it as you can think about it as a motion, as a matter of fact. So so what makes there's an object thrown in the air, and then or moving somehow, then what makes it move away from the tangent line? This, from the point of view of physics, what makes an object turn away from the tangent line? Why doesn't it go straight line? So what pulls the object away from the tangent? Well, the question contains the answer. What pulls? A pull. A pull will pull the object away from the target. A push will pull away the object from the tangent. So what am I talking about?
Force.
The force, yes. So if there is a force, it will or might pull the object away from its straight path. And well, we know that there are no forces. Everything moves along a straight line. Okay, so that's physics tells you. And the force is, so force is a more physics concept. It's easier to understand through the second law of Newton's acceleration. Acceleration, which is the second derivative. So linear approximation, tangent line, is determined by the first derivative, and the presence of the second derivative is what pulls it away from a straight line. Okay, so so the answer is the difference between our approximation. So the difference is determined by how large the second derivative is. Okay, so that's the idea. So this idea now is mathematical idea, right? What makes a difference for a function that what separates a function from its linear approximation? Tangent line, T1, same thing, and the answer is the second derivative. Okay, so and that is, you may have seen this idea in Calculus 1, because in Calculus 1 you may have seen a linear approximation. It also comes with a error bound, and that error bound is expressed in terms of the second derivative. So we are skipping over that, and we go straight to nth approximation, and then you can guess what is the idea will be. So the nth derivative, the nth approximation, the quality of the nth approximation will determine on the n plus first derivative. Okay, so same idea. So let me put it here. So this is the error bound. So f is n plus 1 times differentiable. So that is a prerequisite for a function to have an approximation in the first place. Okay, so that is given, and then we have an estimate. We need an estimate for the for the derivatives between 1 and n plus 1. So we also suppose that we have this inequality. K derivative less than or equal to this number. Let's put an I here. I derivative, k sub I. So so that is my estimate of this derivative. So for all t between a and between a and x. Okay. So x is our, remember just to remind you what these a and x, where they come from. A is the point around which we do approximation. Okay, so once again, it is, if you go back to the to our original example, a was equal to 4 and x was equal to 4.1. So, okay, so a is where we were able to evaluate everything, and we have an our approximation. Then we deviate from that a slightly in some direction. So, but still we still able to approximate. So so we need an estimate for the that extra derivative between on the of the function on the interval between a and x. You can move left or right from that from a. Okay, so that's one restriction, and for some, so where k sub I is some real numbers, some real number. Okay. Where? Okay. Then we have an error estimate. So the difference between the function and its nth Taylor polynomial. Okay, so that is the one that I on multiple occasions drew with yellow. So all of these yellows, this is what I'm talking about. These are vertical lines separating the edges, segments, vertical segments that separate the graph and its approximation. Okay, now we are looking at this algebraically. So that is the error of over the approximation. Okay, and it is less than or equal to kn plus 1. Over here, I is equal to 1, n plus 1. Less than or equal to x minus a, n plus 1 over n plus 1 factorial. So a little bit complicated formula, but really I want you to see that it resembles n plus first Taylor term of the Taylor polynomial. So remember, x minus a to n plus first degree divided by n plus 1 factorial. That's n plus 1 term. Okay, the coefficient that precedes it is determined from the derivative of the function. Okay, so that's how we get Okay, so all right, so that's the error bound. It is a theorem that it takes some time to prove, but we're going to just instead of we'll just use it. We'll just use this theorem to do some things that we have already done. We'll just improve it slightly. We improve it. Well, we improve it significantly, those results, because now we not only just point a finger at a number that is our best bet, we actually know where the truth lies. Okay, so with this, so let me go back to this example. So once again, let me put it in exact same words as before. Approximate. Well, it's not approximate. It's a fancy word. Suppose we don't know it yet. So what is square root of 4.1? And once again, we're doing it by hand. We cannot use a calculator, or we are designing a calculator that should be able to carry out these operations without using another calculator or a computer. So it has to be computed through simple addition and multiplication. So okay, so we will provide a range of values. I want to point out that when we already did it, here it is. No. Here it is. Here it is. Here it is. Right here is the example of square root of. Now let's go all the way. So this was our initial analysis that preceded all the approximations, polynomials, have considered. So all the pictures aside, and the end result was for the linear approximation. The end result was here 2.025. The linear approximation. Then we did a quadratic approximation that was better, but ultimately it is the same computation. Now we know how to do it, except now we can go as many steps as we want. So at this point, let's go with the let's just do the linear one. So we have approximation. We certainly can redo it because differentiation is really not such a big challenge. So this is our answers. We are now our educated answer to this question will be well, you notice that suppose this is what your boss asked you, and then but he did not tell you the standard of accuracy that he wants. But it doesn't mean that you can just throw one number at him. So you still have to provide a range of values because but you don't know what the standard is. You can tell, well, this is my best bet, the range, and I can do better if you want me to. It just takes more time. Roughly, that's how we want to handle it. So this is how we proceed. So in other words, this is how we're going to attack it. Give the range of values under a linear approximation. Okay, so that is our educated. Maybe your boss doesn't know approximations, but this is how we're going to do it. Okay, so so let's redo the linear approximation. The formula is certainly simple. So f of x, remember, is equal to square root of x, square root of x. F prime of x is equal to 1 over square root of x. Proceeding once again to plug in the value, which a is equal to 4. Okay, so f of 4 is equal to 2. I'm sorry, over 2. That's not right. Okay, square root of 1 over square root of 1 over 2 square root of x is the derivative. I plug in 4, so f prime of 4 is equal to 1/4. Okay, so I don't really. I could, well, now let's keep going. So then I'm supposed to produce the Taylor coefficients. So C0 will be equal to 2. C1 will be equal to 1/4. Negative. No, negative. Positive. Okay, 1/4. And so my linear approximation is 2 plus 1/4 x minus 4. Okay. The number, the approximation, will be what is in the center of the range. The range will be an integral. So what is the center of the answer that we have provided is in fact nothing but the central point in that range. So is it the best one? Probably in that sense it's the best, but since we don't know where the truth is, maybe it's not. So then L of 4.1 is equal to, once again, what is 2.025. Okay, but it is just, it lies in the center of our integral. But what is the integral? The integral is found from the error bound theorem. Okay, so we're going to need to estimate. So as you can see, this is the key is n. So we're doing n equal to 1. That's the linear approximation for you. Okay, so which means that we need an estimate for the second derivative. Which means that we actually have to make one more step in that column, down by one row. So we're going to need the second derivative. F of double prime of x is so it's negative 1/2. So it's going to be negative 1/4 x 3/2. Negative. Hold on a second. Where's negative 1/2? Yeah. Okay. Is this right? X 1/2. Negative 1/2 prime is equal to negative 1/2 x negative 3/2. Okay, yeah, okay. Okay? Okay, then f double prime. Well, okay, we cannot plug in. That's the difference of that last extra step. We're moving beyond the linear approximation, but looking at the quadratic approximation, kind of the second derivative, and then we cannot just plug in. Look at the estimate. That is the part that we're dealing with right now. Is this? Okay, the second derivative that we're supposed to estimate is supposed to be within some number. Okay, so estimate what we want to have is it's supposed to be f double prime less than or equal to k sub 2 x here for x within some interval. What is that interval? The interval should contain 4 to begin with, but it also should contain 4.1. Okay, so it seems a bit complicated. So to take that such a small interval, we need an estimate that is easy to compute. But I suppose do we have a root here? Well, I don't think we have a square root here. Okay, well let's just carry it out. Okay, so we need an estimate. So k2 is the one that's k sub 2 is the number to be found. But before that, let's decide what interval we should choose in order that we could choose the smallest possible, but let's choose the one that is easier to handle. No, I think let's take this a small interval. Let's take a small interval. 4.1. Okay, 4.1 is the interval that contains both a as well as 4.1, the point that we're interested in. Okay, so we need an estimate of the function that is right here, the absolute value of that function, when x lies between these two functions. So what does estimate mean? The function looks like, what does it look like? Maybe it looks like this. Okay, so and then this is 4, this is 4.1. The function changes, and we want an estimate, meaning this. Okay, so a number, a bound. So before we get to the bound of the error, we need to deal with the bound of the function of the second derivative. Okay, so our interval that I chose was 4.1. Okay, and so how would you approach it? Finding k2. Well, the picture is suggestive. There is a direct way of picking k2. So this is the graph of the absolute value of my second derivative, which happens to be y equal 1 over 4 x 3/2. Okay, this is x, this is y. Okay, so what's k2? I mean, any k2 will do if it is large enough, but what is the best choice for k2 based on the picture? So is it clear what we're trying to accomplish with at this moment? we're trying to find a horizontal line that guarantees that this piece of the graph, lies below it. The rest of the graph, we don't care. As you can see, the estimate only limits us to some interval between a and x. So x is 4.1, a is 4. Okay, so we concentrate on that little piece of the graph, and we need to find k2, so that the line y equal k2 will be above the graph. So
just k2 just has to be larger than double prime of 4.
larger than what?
At double prime of 4.
That's right. That's right. Because what the idea here is, choose k2, any number larger than or equal to, just as well equal to, f double prime of 4. Why? But in other words, this value. This is f double prime of 4. Why? Why? Can you? The picture suggested, but can you justify that choice? The function is decreasing. The function that I intentionally plotted a decreasing function so that it's clear what value to pick. Can you tell why the function is decreasing in the first place? That function. It's 1 over x 3 halves, right? So we know that from calculus 1 that it will go like this. It is decreasing. It has an asymptote, so it is a familiar function. So we can justify that this is larger than or equal to f double prime of x for all x larger than 4 because it is decreasing. The function is decreasing. It lists on this interval. Okay, so that's kind of analysis that if you have function decreasing or increasing, then you know for an estimate, you pick the value on the left end of the interval or the right end of the interval. It's going to do the trick. Okay, in general, then if it behaves up and down, then it might be more complicated. But this one is decreasing, so we just pick that number, which happens to be so what is k2 then is equal to where is it? 1 over 4 times 4 3 halves. Okay, so 1 over 4, what's 4 to 3 halves? 8. 8, so 1 over 32. So that is our estimate. Okay, so that is a k2 that we're looking for. Now we can use our theorem and plug it into the last part of our theorem. T, and I put an L, but let's match this with the theorem. So this is T1. T1, the linear approximation. That is the crucial part of our computation. This one is also T2. Okay, so T2 as well. Okay, so then we know that T2 of, or rather f of x, well, let's do f of x first. F of x minus T1 of x. Why is it T2? It's a T1 over here. T1 is, by the theorem, we have less than or equal to k2, let me just write it out, x minus a and n plus 1, which makes it 2 over 2 factorial, which is k2 is 1 over 32. This one is x minus 4 squared over 2. Okay, so a is 4, x is to be determined, not to be determined, but rather this is just what the theorem says. Now we choose x equal to 4.1. That is our point of interest. So we have then what? Square root of 4.1 minus T1 of x, which we already determined to be 2.025. Okay, less than or equal to this number, which is 1 over 64, and this is 0.1 squared. That's our error, and it is a fairly small number, so it is 0.01 divided by 64, and we can now use a calculator to compute it. Okay, 0.01 divided by 64, 3 zeros, 156. Okay, so that's how close we are, how close this number is to the truth, or not how exactly close. It's not literally the distance between the two numbers. We don't know what this is. This is still an unknown number, so how do we interpret this conclusion? So what do we provide now? What do we send to the boss? This is the last computation, so what's the answer? Plus or minus this number. So you either say 2.025 plus or minus 0.000156, or you can actually carry out the computation and give an interval. Let's do both. So the answer is 4.01 is equal to, or I don't know, equal probably, I still use these terms, or, depending on what kind of boss you're dealing with, 4.1 square root is in the interval. Okay, let me carry this out. 2.024. Okay, let's subtract. So what is it? 844 is it? And 2.0525156. Okay, that seems reasonable. So that way, you can actually know whether or not you are falling into within some specifications that you're supposed to satisfy. Because if the range is outside of the tolerance, the error might be too large, and so that the bridge might collapse, or a plane might break apart in the air. Okay, so we'll talk more about this next time.